Hello, Precalcsters. In this video, I am going to be running through our Chapter 5 practice test. And one of the things I'm going to do, just in the interest of my time and hopefully yours, is I will certainly show all my thoughts and everything, but I'm not going to show the calculator work, which I've completed ahead of time just to try to save a little bit. So remember to pause periodically as we go through this so that you can double check that you're also comfortable using the calculator to answer these questions. So without anything further, we'll go through. Remember, please pause, email me if you have questions about stuff, and the more specific, like if you have a picture and saying, I don't know where I'm going wrong, that makes it really easy for me to come back and reply and hopefully help. So for this, I'm doing it on Word. Hopefully we don't get any weird issues showing up with using this. Anyway, here we go. So on the first one, we are asked to find the exact value of sine and cosine for the following. And this first one, I've hooked you up because 285, unfortunately, does not show up on the unit circle. But what does is 315 and 30. So this right here is the telltale sign that, yep, we should be using the sign on part A of a difference. So right off the bat, I'm just thinking that this is U, and there's the word issues that we talked about. We'll do that later. This is my U right here, and this is V, or alpha and beta, like we used before. But let's just plug into the rule. So we know that the sine of 285, which is what we're after, is really the sine of 315 minus 30. Okay, deal. And those are both degrees. So we're just going to expand this here, and I know that that is sine of u times the cosine of v, which will be the sine of 315 degrees, and the cosine of v, which is 30 degrees, minus, and minus because it's minus here, and that's how I remember it, the cosine of 315, the cosine of 315 degrees, and the sine of 30 degrees. Okay. Now, for each of these, and this is that calculator part, I just want to really specify that I'm not showing all these. If you are struggling to follow along, I would encourage have a unit circle in front of you to make sure you can get these values, but I'm just going to blast through. So the sine of 315 per the unit circle, and every single one of these is per the unit circle, so I don't have to keep repeating that. Let's see, that is a negative root 2 over 2. And the cosine of 30 degrees is a solid root 3 over 2. Minus the cosine of 15 is a solid, 315 is root 2 over 2. And the sine of 30 degrees is 1/2. So we're just going to multiply these fractions straight through numerator, numerator, denominator to denominator. So let's see, this top one here, since they're both in the radicals, negative root 2 times root 3 is a negative square root of 6 over 4, minus this one is going to give me the root 2, the square root of 2, over 4. And then all we're going to do is write this as a single nice answer. And I'm not trying to slide down all the way, which looks like on this one, a single expression to be able to express this, negative root 6 minus root 2. We can't combine these into a single expression, all over 4. And we're done. Now, each one of these is worth a different number of points. This one was worth 2, which 1 point from did you try it with the correct formula. So I'm just going to say formula, and that's the sum or difference that was required. And then your other point would come from the answer on part 2. So I'll switch color for each one of these. So let's look at this one. 5 pi 12ths. Now, this can be a challenge, and I know that some people struggled when we did this in class. When I think of 5 pi 12ths, I don't have a good idea in my head of what I need to add or subtract to get there. But what I do know is that this is a quadrant 1 angle, because 6 pi over 12 would be pi halves. So I know that this is in quadrant 1. So what I think of is the things in quadrant 1, how could I write them with a 12 in the denominator? And what I mean by that is if you check the unit circle, pi 6ths is in quadrant 1, and that becomes 2 pi 12ths. And I'm only doing this because I need to find a way to add or subtract to get 5 pi over 12. So there's pi 6. I can do the same thing, and I'll use separate it with a semicolon. I can do the same thing for pi fourths, which is going to become, when I multiply by 3 over 3, 3 pi twelfths. And at this point, I probably wouldn't go any further, because what I recognize is if I want to get 5 pi twelfths, I just add up 2 pi twelfths and 3 pi twelfths. So I would use the sum rule is what I would be doing here. Now, if you wanted to use something else for whatever reason, you could say pi thirds becomes 4 pi twelfths. And this one immediately doesn't seemingly help a ton. But remember, we could go a step further. We could do 2 pi twelfths. 2 pi thirds, which would sneak us into quadrant 2. And I'm probably going further than I need to. And 2 pi thirds would be 8 pi twelfths. And the only reason I'm expanding here is I would like to, for this problem, say the sine of 5 pi twelfths is equal to, and I would just use the sum. Sorry, we're doing the cosine here, so let me fix that. The cosine of 5 pi twelfths. Based on these first two values that we found, I would rewrite this and think of it as the cosine of pi sixths. My 2 pi twelfths is a variation, plus pi fourths. That's how I view this problem. But it's worth noting, and totally optional, that if for whatever reason you didn't like that, I think that we could do 2 pi thirds. And I'll erase this one here in a second. This is just me talking, which is this, 8 pi twelfths. And I could minus pi fourths from it. And we could use the difference rule instead of the sum rule. And that would be completely fine. Now, there are other variations of this that exist out there. I don't know that anybody would use that. But just worth noting, and this is the last one, I'll switch color. I am going to ultimately use the cosine of a sum, but I do want to highlight that 5 pi twelfths is exactly the same thing as saying, and I got to think this out, 10 pi twelfths over 2, which is 5 pi 6 over 2, and we could use a half angle formula. Not required, not needed, but we could. 5 pi 6 over 2. And this, we could use a half angle. We're going to get a different looking answer, but it does exist. Now, I have said all of that, and I'm going to clear everything that we didn't need. So if you need to rewind it, please do so. I'm going to stick with the cosine of a sum because it's the most natural, easiest choice to make for us. For me, and hopefully you, but we'll see. So let's just expand this. I know that the cosine of u plus v is cos u cos v. So it's a cosine of pi 6 times a cosine of pi fourths minus, we switch the signs, and I'm going to switch this blue. Sorry, it's going to be annoying mid-problem, but the sine of pi 6 times the sine of pi fourths. Okay, so looking at these, I'm just going to kind of blast through. Again, this is a unit circle that I would suggest you use. What we wind up with here is, well, let's see, cosine of pi 6. Let's think that out. So the cosine of pi 6 is root 3 over 2. And unit circle is where I would use these. Cosine of pi fourths is root 2 over 2. Minus the sine of pi 6 is a 1/2. And the sine of pi fourths is root 2 over 2. So again, all of these are just lining up directly here. And it looks like we get a very similar looking answer. And I'm just going to do this in one step here. We will get root 3 times root 2 gives us the root 6. And what I'm recognizing is this is going to be over 4 right here. And this is going to be over 4, so I'm just going to shove it together. And here we go. Minus root 2. Now, I want to highlight here, because this is a weird thing that happens from time to time. This is a complete coincidence that, sort of a complete coincidence, that it's so close to our original answer. Unintentional. Maybe they should be if we looked at it a little bit closer. It's okay that they're close. I just want to make sure that we're not thinking that they're the exact same, although they're close. Slight differences. These values show up all over the unit circle, so it makes sense that they show up here also. Cool. All right. So there's that one. For the second part, just so you know, if you're giving yourself like a score, there was 1 point for did you try with a valid formula? Now, it could have been the sum, the difference, or whatever. Did you use that formula correctly? And did you get the right answer? Now, I know that these two are kind of the same, but I'm looking for really, did you say the cosine of pi 6 was root 3 over 2 instead of 1/2, which is a pretty common mistake. Cool. So were there 5 points there? All right. On number 2, here we go. I give you a little place to draw some sketches. So here we go. I'm going to sketch 2 triangles. The first one we'll do in blue because U is in quadrant 1. And let's see. Here's a quadrant 1 triangle. And there's my angle U. And let's look. If the tangent, which is the opposite over the adjacent, is 3/4, then here's the opposite and the adjacent. And I know off the top of my head by Pythagorean triples that this is a 5, but you could confirm that with Pythagorean theorem. Now, the only reason that we draw these, and I guess the big reason, is we want to be able to keep stuff straight. So next to this, what I'll do is I'll say, okay, the cosine of angle U was so ka toa, adjacent over hypotenuse, is 4/5. And the sine of U I'll need in these equations is opposite over hypotenuse, which is 3/5. Okay, we have triangle for U drawn. Let's do the same thing for V, and I'll do this in green. V is a quadrant 3, and I think bow ties and butterflies with this. So the hypotenuse sneaks into quadrant 3. Here is angle V, and we're told that the cosine is negative 4/5. So adjacent is 4 and 5. And if we think about this as the origin right at the tip, which is what I hope you do, we'll recognize that's our negative 4. And in turn, this must be a negative 3. And that, again, is a Pythagorean triple or Pythagorean theorem. And just working with the understanding that we're in quadrant 3 requires a negative y value. So we have those, and I'll do the same thing here. The cosine of angle V is adjacent over hypotenuse, which I know we already had that, but it's negative 4/5. And the sine of angle V is opposite over hypotenuse, which is negative 3/5. So these sketches are worth a point, and we have to have them. Now, kind of. We need these values, cos U, sine U, cos V, and sine V. I hope you include the sketches. Include the sketches. Never mind. So, looking at these, I'm just going to plug and chug through this. So I know that this formula will become, and I'll do this one in black here. I lied. We're going to do a more fun color. We'll do orange-ish. I think that's orange. All right. So check it out. This is exactly equal to sine U cos V plus cos U sine V. Okay, so now it's just a matter of plugging and chugging based on this work here. So the sine of U is 3/5. The cosine of V is negative 4/5. Plus the cosine of U is 4/5. And the sine of V, we'll put here, looks like it is negative 3/5. And something awesome happens with these. Let's just check. I know that in the end, everything is over 25 because they're both over 25. And then we have this part gives us negative 12 plus negative 12. Look at that. We have negative 24/25. If you need an extra step in here, I would encourage do that. But I'm trying to make this video on the shorter side rather than longer side. Okay. So just, 1 point for the picture, 2 points. Did you try and use the right values from your pictures, and did you get the answer? Okay, this one here, cosine, and this is going to change. It always does, but we're going to think of cosine as I don't know, what color haven't I used? We use bright red. So cos U minus cos V is exactly cos U cos V plus sine U sine V. And whether it's alpha and beta or sine or U and V, doesn't matter. But same thing, once we have these pictures from the appropriate quadrants, this is just a plug and chug. So cosine of U is 4/5 times the cosine of V is negative 4/5. And maybe this time I'll take it a little bit differently. I'll just work this part first. That's negative 16/25. Plus, And then we're going to work this line now. Sine of u is 3/5. And sine of v was negative 3/5. So I'll just say that's plus a negative 9/5. Sorry, 9/25 because we multiplied. And then lo and behold, this becomes negative 25 over 25, which is our answer, negative 1. And 2 points for this one. Did you use the values from your photo or from your picture, your sketch, or whatever you want to word it? And did you get the right answer in the end? Cool. Baller. So this was totally worth 5 points in the end. Awesome. All right. So moving on to the next one, we are verifying some identities. Now, looking at this one, I'm going to be honest, I have a key in front of me, but I'm not going to look at it at all while we're doing this one because I want to make sure I can emulate that even if we don't know exactly where to go, taking some steps will be sufficient for us. So let's see here. Oh my gosh. I just oh my gosh really loudly because my computer's trying to restart and maybe it didn't actually restart, which would be awesome. Oh, thank goodness. I'm very glad profanity didn't spit out there. So here we are. I think this side looks harder. And what I realize is it's the cosine of a sum. So I'm going to reference my sum rules for these, the cosine of a sum. And I know that that is cosine of the first. So cos x times the cosine of the second, cos pi halves, minus sine x sine pi halves. All right, so there they are. And I just want to make sure, again, this is going to be like a broken record. Unit circle will convince you that that is a 0, which means all we have left is negative sine x. And this whole thing goes to 0 because we multiply by 0. We have negative sine x times the sine of pi halves. And if I think about the sine of pi halves, it's a 1. And look at that. We're done. We have proven it. All that this took was recognizing that there's a sum rule and doing the sum rule, and it works out nicely. All right. On the second one, I think that this side looks uglier. 2 points for the first one and the second one. Did you try it like authentically and legitimately, and did you get it right? Okay. For this one, I think this side looks uglier, although I do recognize that we have a double angle weighting here that might be useful, but we'll use that if we need it. So this left side, in my mind, looks uglier, and it's going to look ugly because we have to square stuff. So let's do that. Sine x, and I'm going to show some scratch work here. Sine x plus cos x squared literally means times sine x plus cos x. Now, most of you, I imagine, may foil this just in your head, but let's just see what shakes out. So we get a sine squared x, and then I'm going to say plus sine cos, so that's plus 2 sine x cos x. And then we're going to do the last part is plus cosine squared x. Okay. I am going to rearrange physically on the page. I'm going to move this one in this one's place. We're just going to rearrange. So we get sine squared x plus cos squared x plus 2 sine x cos x. Now, annotations, I expect everybody to be able to follow. This is the place where I think annotations might be useful. Now, I'm going to just change my color, and I actually hit the wrong button, so I'll change more than the color, apparently. But I want to notice something. This right here is an identity, and it's very specifically the Pythagorean. So I know that I'm going to use the fact that sine squared x plus cos squared x equals 1. Additionally, this little piece, if you don't recognize it right off the bat, that's okay, but this is a double angle. This is exactly the double angle. This is what we get and what happens when we expand the sine of 2x. So we're just going to use both of these identities together, and all of a sudden, this thing is just going to shake itself out and be done right here, right now. So by rearranging, I recognize that I can write sine squared plus cos squared right here as a 1, because it is, and then plus And instead of 2 sine x cos x, we're going to use the double angle and say that, oh yeah, that's just the sine of 2x, which is exactly what the right side was supposed to be. And we're done. We are proven. Cool. Baller. Okay. These two problems, looking at them, they're fairly nice. And I don't want to say necessarily in contrast because the other ones I don't think are bad. But I love when problems ask me to solve, and it's this because it makes it so much easier. So we're just trying to solve. And I recognize that we have a something that's kind of like quadratic type. So I'm going to make this a quadratic where we just set it equal to 0. So I will subtract a cosine x and a 1 from each side. Minus cosine x and minus cos x, minus 1 and minus 1. And then let's just see. We get a lovely quadratic that takes the form 2 cos squared x minus 1 cosine x minus 1 is now equal to 0. And I know that some of us factor differently. So just as a review, if I'm factoring this and I'm using grouping because the leading coefficient is not 1, I multiply these. And I get a -2, and then I'm thinking of factors of -2 that must add up to this coefficient on the cosine, which is a -1. And I think it's -2 and 1. Now, I'm going to rewrite this 3-nomial as a 4-nomial to help me group. So we get 2 cos squared x, and then I'm going to replace these with a different color just so they stand out a little bit. Instead of minus cosine x, I'm going to have minus 2 cos x plus a 1 cosine x. So that's still my minus cosine x if I were to combine them back into nice like terms. Minus 1. Still all equal to 0. Now, by changing this to a 4-nomial, we get 2 equally sized groups from which we can pull out GCFs. This one, a 2 cosine of x, comes out, and it leaves behind a cosine x minus 1. This one is already cosine x minus 1, which means the only thing I can factor out that leaves that the same is a 1. So I'll factor out a positive 1. Still equal to 0, which means I can see 2 factors. The first factor comes from these two. I messed up. The first factor, here we go, comes from this piece and this piece. So we get 2 cos x plus 1 is one factor, and the other factor comes from these pieces that match. So we get cosine x minus 1. Now, I think you had hopefully a little bit more space than I do because I'm writing fairly large on this thing, but it's still all equal to 0. Now, this is unit circle stuff. I'm going to work just right here to save a little space, and I'll put my answers here. I'm thinking this out. If I have the 2 cosine of x plus 1 equals 0, and I'm going to do some scratch work that I will erase, just so you know. So I'll do the scratch work here, but I'm going to erase it so I can see it on the next problem. If we have one factor equals 0, I will subtract 1 and divide by 2, and we're really just trying to find when is it true that cosine is -1/2. Now, on the unit circle, there's 2 places where this happens. It happens at 2 pi thirds, and it happens at 4 pi thirds. So we'll just list both of those answers here, since those are both... Ooh, am I wrong? No, I think I'm okay. Let me double check the problem that I'm working here. 2 cos squared. Oh, yeah, I was looking at the wrong thing here. Yeah, 2 pi thirds and 5 pi thirds. I'm sorry. So x equals 2 pi thirds and 5 pi thirds. And those, should it be 5 pi thirds? It should be 4 pi thirds. -1/2, it should be 4 pi thirds. Pi thirds, 2 pi thirds, I'm sorry, for -1/2, and 4 pi thirds for cosine to be a -1/2. Now, the other factor was cosine of x minus 1. So I'm going to do a little bit more scratch work. Cosine x minus 1 equals 0 is simply saying find the x's where cosine of x is equal to 1. And the good news is that there's only one place on the entire unit circle where that happens, and it looks like that is at 0. And we have it. 2 pi thirds, 4 pi thirds, and 0. And we're done. Okay. Now, only in the interest of the space, and I'll make sure that on the actual test, you guys don't run out of space with stuff. but I'm going to work this one here. Now, I'm just going to expand this one right off the bat. I'll tell you, it's a double angle formula, and I'm going to use that to my advantage to try to make this quick and easy. And I'm actually going to zoom in so I can write a little bit smaller. So we'll zoom in, and here we are. So I'm going to expand the sum and the difference rule for these signs. And this is one of our formulas. I know I get sine x cos of pi fourths, and I'm only doing the first one right now, plus cos x sine of pi fourths. With the understanding that these cos of pi fourths and sine of pi fourths are just numbers. Now, I need to subtract off of this, and I want to make sure I don't goof up the signs, because I know that it's going to get weird, like the signum, positive or negative is what I mean by that. So I'm going to expand this one as well. Sine x cos pi fourths, cosine of pi fourths, minus cosine of x times the sine of pi fourths. And I know that after all that is said and done, according to this equation, it should be equal to 1. Now, couple ways that we can go through this, and it doesn't matter to me, really. We could just plug in numbers for cosine of pi fourths and sine of pi fourths, because we can find those. Or, there's another thing I want us to recognize. I have sine x cos pi fourths minus sine x cos pi fourths. These two are just going to fall out. They're just gone. They just straight up disappear. Now, I also have a cos x sine pi fourths minus a negative cosine x sine of pi fourths. So I really have two of these. So I'm just going to simplify this down. I have 2 cosine of x times the sine of pi fourths. And that's through distributing that negative. And I now know that that is going to be equal to 1. Again, I just want to stress, minus a negative, I just added these two together. And since they're exactly the same, I now just have 2 of them. Okay, so little steps from here. We have 2 cosine x times the sine of pi fourths, which is root 2 over 2, equals 1. I notice that that happens, and we now have root 2 times the cosine of x, or cosine of x times root 2, however you want to think about it, equals 1. I will divide both sides by root 2. So we get the cosine of x then is equal to 1 over root 2. And then in a different color, just in case we need it, I'm going to rationalize by choosing a clever choice of 1 to fix this. And what we really wind up with is then that the cosine of x ought to be equal to root 2 over 2. So here we go, cosine of x equals root 2 over 2. And here we are, between 0 and 2 pi, I just need to think of where does that happen. Well, there's only 2 places where cosine is positive root 2 over 2. And confirm this on the unit circle for me, but I believe that the first place happens when x is pi fourths. It does not happen at 3 pi fourths because it's negative. It does not happen at 5 pi fourths because it's negative, but it does happen one more time at 7 pi fourths. And we're done. Cool. Okay. Baller. On to number 5. We are trying to find the sine and cosine of u over 2. And the cool thing is that this formula, as ugly as it is, all we have to be able to do is think out where these things live. Now, in class the other day, like we don't need to draw a picture here, but here's what I want to think out. This little statement tells me that angle u that I'm working in is in quadrant 3. Okay. So in quadrant 3 is u, and I'm going to cut it in half. Now, the way that I think about these is I think about the largest angle in quadrant 3 that I could pick that's nice. And I know that quadrant 3 runs from 180 to 270. So I might think something like 268, and only because it's nice and easy to divide in 2. If I cut that in half, I get 134, which would be a quadrant 2. And the reason that I care about this is if I'm trying to find the sine of u over 2 and it lives in quadrant 2, then it's going to be a positive. Now, I would also check the smaller side of that. 178 is a nice angle in 182 is a nice angle in quadrant 3 that I could cut in half. So if we do the same thing here, and I keep changing the thickness on accident, but if we take a small angle in this quadrant, which is like 182, and divide it by 2, we get 91, which would again be a quadrant 2, ensuring that my sine is positive and my cosine, I guess for a different one, my sine is positive because this is a different angle over here. Okay, so let's do this. I know that I'm in quadrant 2 for u halves. Cool. Done. Piece of cake. If we're in quadrant 2 for this, let's just think it out. And I'm going to help myself out by drawing u to begin with. This is not u over 2. This is u. And I know that the tangent is 4/3. So quadrant 3 makes sense. -4. Just kidding. Sine over cosine. Should have this as, or opposite over adjacent, however you want to think about it. Opposite is a 4. Opposite is a 3. And I recognize that they're both in this quadrant 3 because we're talking about u, and that our hypotenuse would be 5. Now, only reason I'm doing all this and I'm thinking about the picture is because when we plug into the formula, the sine of u over 2 that we're about to use, this half angle formula, this is plus or minus, which we just decided that our half angle is in quadrant 2, so I know it's the positive variation, is the square root of 1 minus the cosine of u, which if I'm looking at this, and really important here, cosine of u is adjacent over hypotenuse, it's -3/5. This is the cosine of angle u, and this is all over 2. Now I'll write it over 2 here. The very next line, I guarantee, instead of dividing by 2, it's going to be called multiplying by 1/2 because it's easier and nicer to look at the math. So let's see, this changes to 1 plus a positive 3/5. So that's 1, which is 5/5, plus 3/5 gets me to 8/5. So I have the square root of 8 over 5. That's just these two right here added up in common denominator. And then over 1/2. Or sorry, over 2 is just multiplying by 1/2. Okay, so let's just see what happens here. This becomes positive the square root of 8 over 10. 8 over 10. And I can simplify this further if we really want. I could have called this 4/5 equally as well, but I'll just simplify it here. That is 4 over 5. And then we need to do a little bit of cleaning, just a little tiny bit. The square root of 4 is just a 2, and I'm over root 5. I just did the square root of a fraction. It's a fraction of the square roots. And then one step away with rationalizing. If you don't rationalize, your answer is technically correct, but I will not give you full points. It looks like we get a singular value of 2 times the square root of 5 over 5. And we're done. There is the sine of u over 2 for this particular angle u. Now, the second one is the same thing. It's just a nicer angle. We are in quadrant 2 because it's pi halves to pi. That's where u is. So I'm going to start this one differently just to show you we can still get there. I know that quadrant 2 is where angle u lives on the second problem. And I know that the adjacent over the hypotenuse is -2/7. And I'm going to do, I'll show the Pythagorean theorem. -2 squared, I'll put parentheses there, plus y squared, which I'm going to call this y for now, equals 7 squared. Which means a little bit of quick math here. I think we can probably all agree that y squared is 45. Which means that y, if we clean this up, is the square root of 9 times 5, which is 3 root 5. Okay, I've Pythagorean theoremed here. There's 3 root 5 on this side. And again, the only reason I need that is because I know I'm going to need a cosine of u in my half angle formula. So if we're trying to find that, let's see, the cosine is adjacent over hypotenuse, and we already had it. Maybe I didn't need to do any of this, and I should have skipped it, but we'll be okay. So let's use the cosine of a half angle. Cosine of u over 2 is plus or minus, but again, I'm going to think back to this. If u is in quadrant 2, then half of it must be in quadrant 1. Pick any angle in quadrant 2 and divide it by 2, and you always wind up in quadrant 1. And in quadrant 1, cosine is positive. So I'm going to include this. Now, computationally, I don't normally ever actually write the over 2 part. Right here on this first line, instead of writing over 2, I'm going to think about it as multiplying by 1/2. So we're just going to do it like that. I know that this becomes, for cosine, it's 1 plus And I'm going to make that the right size because I just said I was going to do it, and then I changed size. I know that this becomes 1 plus the cosine of u, and the cosine of u in ours is -2/7. And again, instead of writing over 2, I'm just going to say times 1/2 right here because it makes it work a little bit nicer. In my opinion, you do not have to do this. You can keep it a fraction. So let's see. 7/7 minus 2/7 looks like it's 5/7. That's in the parentheses, still times 1/2. And it looks like I'm going to get the square root of 5/14. So plus the square root of 5/14. And I'm just going to split it up here so that we have room to rationalize one more time. So we'll rationalize with this blue color. I think that a clever choice of 1 will come in this flavor. Always a radical over itself. And let's do a little, see if I can't do this math correctly. 5 times 14 is 70. So it looks like I get the square root of 70 over 14. And we're done. And it's positive and it's nice and done. All right. So blasting through here. Couple more that we're going to knock out. Okay, these ones are really valuable when we get to calculus stuff, and especially some hard problems in calculus get a lot easier if we do this. So let's see. We're trying to take this f of x and make it a thing that says f of theta instead. So let's just see if we can make that happen. So here we go. We're between 0 and pi/2, so we're quadrant 1. Nothing weird happens with it. And let's just see what shakes out. If instead of x, I'm using 4 secant theta. So here we are, 4 secant theta squared, because it was x squared, minus 16. And now it's just the algebra game. If I take 4 secant theta times 4 secant theta, I'm going to get 16 secant squared theta minus 16 in the end. Okay, things are looking real nice right now. I noticed that we can take a 16 out of each of these two terms, and it would leave behind a secant squared theta minus 1. And this is via just regular factoring. And I'm going to take the 16 square root right now since I have it. I know the square root of 16 is 4, and then I'm going to use a little Pythagorean identity. Secant squared minus 1 is just a fancy way to write tangent squared. And if we do this, we're at our final line here, and I wrote that, but I'm going to make this f of theta, and we'll just say that was a happy little accident. Well, the 4 was already here, and the square root of tangent squared is tangent. And we have successfully now completely rewritten this awful thing as a singular function with theta as its variable, and it's nice. If you struggle with this, it is 100% Pythagorean identity. Be prepared to use them. You will be using them, I assure you. All right. The very last problem that we have. This looks awful. It's not. And there's actually a lot of really cool stuff going on here. Little comment. You may or may not remember that this is a difference quotient. We saw these earlier in the year. Not relevant necessarily to the test right now, but this is what we're evaluating. And we did this right away in chapter 1. I know it's been, a long time, but this is the trig version of this happening. Now, I don't know which side you guys think is uglier, and I honestly don't know which side I think is uglier. I'll tell you, my gut says this side, the left, is the uglier, but we'll see what shakes out and see if anything nice happens. So when I'm looking at this one, on the left is where I'm starting. I'm going to think, well, the sine of x plus h, that expands. And that's the sum rule. The sine of x, the cosine of h, plus the cosine of x and the sine of h. That's how that expands. But I still have a minus sine x. And that looks like it is all over h still. Nothing changed. Now, these don't really match super nicely, and that's okay, but I do want to notice just one quick little thing. Maybe I don't see anything obvious that happens here. Now, I know I could factor a sine x out of this and this, but I can't factor a sine x out of everything. So maybe I've made the wrong choice. Now, I don't see anything obvious that we can do, and whether or not that's fully true or not isn't the point. But you might not. And if there's nothing obvious that happens, a valid thing to try would be switch to the other side. Remember, don't erase stuff. So let's see. If I just try to clean this one up a little bit nicer, let's just see. Cos x sine h over h is what this turns into, because I'm just saying that's over 1, and I'm just multiplying. So I get a cosine x times a sine of h all over h minus, and I'm going to distribute this one in, because again, that's really over 1. And let's just see, we get a minus sine x, and then plus a sine x cos h. And that's all over h. So that was over h, and that was over h. Which means, well, gosh, let me just see if I can write everything over h really quickly. And I'm going to rearrange it for no reason. I'm going to write this one first, and maybe there is a reason. Sine x cos h. And then I'm going to write this one second, because I can rearrange, and I'm doing this, there is a reason, I assure you. Cos x sine h. And then the only thing we had left was this one, which is minus sine x, I'm sorry. And if you take a little step back, I just want to check something. I'm going to switch color. This matches this. And plus cos x sine h matches this, plus cos x sine h. Minus sine x happens to match minus sine x. So what we've done is, by taking a singular step on both sides, we have made these matches, made these sides match. So therefore, the identity is proven. Now, here's my little fun extension that this is purely optional, but I will give you aura for this if you bring this back questioned. A follow-up that is not required, but if we let h, what happens? I'm going to write this as a question. What happens to this if h approaches 0? Now, this is a little calculus extension, which I'm going to show you just a notation. If I let h get really small, what happens to cosine of 0? And what happens to the sine of 0? And dividing by 0 is essentially like, that's a weird idea. This is not required, but I do want you to know that this question that I'm asking, the mathy version, is written as the limit as h goes to 0, which is just saying, hey, look, h is going to 0 of this lovely thing. Now, I would encourage, if you're going to do this, I would use the right side. So we'll say it's the cosine of x, and I'm going to make this here. The cosine of x. And I would check it with this side, sine h over h. Lost my train of thought, sorry. Minus the sine of x times 1 minus the cosine of h over h. And I don't know that you guys will come up with the answers, but if you do, I will. I said aura a second ago. I'll give you a homework pass if you're watching this video and you do this problem and you can explain it to me. I will give you a late homework pass. Not a free homework pass, but a late one. Cool. All right. Again, please reach out if you have questions about anything from this video. I'm going to scroll through it one more time really slowly just so you have one final kind of look at it. Don't forget the test is going to be on Monday. So theoretically and hopefully we have 12 views to this video, but time will tell. And I'm just going to go through really slowly back through everything. I'll zoom out just a skosh. I quit including the points. Sorry. So we'll just go through really slow and we'll just see what happens. All right, everybody, remember as you're going through, if there's something that I did, I don't think I made any mistakes, but It does happen from time to time. If you're working this and there's something you don't understand, please send me a picture of the work that you've done and the specific question. And if you just shoot me an email, I will send you a whiteboard answer back where I work and I help you find your mistake, hopefully without just telling you. But cool. 45 minutes to really go through everything in detail. I hope that you guys are able to do this in an hour and 15, somewhere in that range. And yeah, prepare for the test on Monday. See you cool cats and kittens then. Peace out. Enjoy the weekend. If the wind stops, go build some snowman or snowboys or snowgirls or whatever you call them. Peace out, A-Town.